Here is another NMR structure determination problem. I will show you all the data, and then you should pause the video and attempt a solution on your own, and then press play and you can watch my proposed solution. Here we have the proton NMR spectrum with FEMP formula C9H8O4. There's also a broad 1H signal at 11 ppm, which I did not show here. We have these four signals here, and then we've got a 3-hydrogen singlet at around 2 ppm. Looking at a blow-up of the aromatic region, you can see at 8 ppm there's a doublet of triplets, and we got a really tiny triplet, a larger triplet, and then another doublet of triplets. Looking at the carbon spectrum, we'll see there are 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. So we have 9 different carbons here, and they range from about 170 ppm down to about 25 ppm. So go ahead and pause this, rewind, and look at the different pieces of data, come up with your own solution, and then press play again, and we'll work forward with my proposed solution. First thing I would like to do is calculate the HDI, and so that's going to be 9 times 2 plus 2 minus 8 all over 2, and so that's 18 plus 2 is 20 minus 8 is 12. 12 over 2 is 6. So I have 6 HDI. 4 of them probably come from the aromatic region here, and that means I have 2 carbonyls or additional C-C double bonds or rings. Given that there are only 9 total hydrogens here, so more rings are unlikely. I can also observe that I have 4 hydrogens, 7 hydrogens, 8 hydrogens if I count up the proton signals, and that gives me the same number that I have in the formula. So there's no symmetry at all in this molecule. The next thing I can recognize is the aromatic region is telling me that I have a di-substituted aromatic ring because there are 4 signals here. I can also recognize that I do not have the para substitution because there is no symmetry within the aromatic region. I have 4 distinct signals, so I don't have para substitution. That means I have either ortho or meta substitution. And we can talk more about what we have when we go look at the aromatic region a little more closely. And then the last thing, well, 2 more things here. The 1H signal at 11 ppm is probably indicative of a carboxylic acid. And if we draw that like this, we can observe that that accounts for another HDI and another carbon. And then the 3-hydrogen singlet at about 2 ppm is definitely a CH3. And we can observe, because it's right around 2.1 ppm, it might be right next to a carbonyl. That's pretty often we'd have a methyl ketone or a methyl carbonyl of some sort. So I'm going to predict that this methyl group here is part of a methyl ketone, or at least next to a carbonyl. And then this signal here is our carboxylic acid. And importantly, the signal at 2 ppm gives me another HDI factor, right? This is a second carbonyl. So if I have 2 carbonyls plus the aromatic ring, that is a total of 6 HDI. So let's move on to the aromatic region for now, and we'll figure out which substitution pattern we have. Is it ortho or is it meta? All right, a few things we want to observe here. We've got, let's see, this would be called a doublet of triplets. This would be called a triplet, triplet, doublet of triplets. Now remember that a doublet of triplets means that the hydrogen that created this signal has both a single nearest neighbor and 2 nearest neighbors. So it actually has 3 nearest neighbors, which would make sense if we had 4 hydrogens on a ring. This was one of them. It would have 3 other hydrogens on that same ring. This really narrow triplet implies that there are 2 nearest neighbors for this hydrogen. The really broad triplet, again, implies 2 nearest neighbors. And then in this case, again, we imply basically 2 different types of hydrogens as nearest neighbors. 1 closer, single hydrogen, making the doublet, and 2 a little further away, making the narrow triplets. Also to consider here is the difference in spacing. The coupling constant, or sometimes called the J value, on this triplet is very wide, and on this triplet is very narrow. The three lines are almost all together, and we can make a note of that. So narrow J value, and we might just call this one a larger J value. And as you remember from the textbook, the J value, or the coupling constant, gets larger as the hydrogens get closer. So that information tells us that the hydrogen making this signal has two close nearest neighbors, whereas the hydrogen making this signal has two far nearest neighbors. So let's write that down as well. 2H is near, 2H farther away. And let me draw the ortho and the meta rings, and we can see which one might make these four signals as we see them here. So what I'm going to look for is a hydrogen that would have two nearest neighbors, and certainly this one has two nearest neighbors, but it also has a further neighbor. So it might not be just a triplet, it might be a triplet of doublets. This hydrogen has two further neighbors, but nothing really close by. So that might be that really narrow triplet. This hydrogen here has two close neighbors, but nothing a little further away. So that might be this larger triplet. So I'm thinking we probably have the meta. So let me start to maybe put in some color coding here. I suspect that this signal at 7.5 or so is this red H, because it has two neighbors. It doesn't have anything a little further away that might cause it to have tighter splitting values. It just has the two neighbors. And then if I would get some green here, this hydrogen is probably that one. This one has no nearest neighbors, but it has further neighbors, and that would give us this really narrow triplet here. And then we'd have these two hydrogens, these two signals at 8 and at 7.3-ish. I'm not really sure which is which. It doesn't really matter at this point because I think we've got enough evidence to support the meta substitution pattern on this ring. So the what we would call maybe an apparent doublet, triplet, triplet, and doublet is a pretty common substitution, or I'm sorry, pretty common aromatic region pattern that indicates that we have a meta substitution pattern. Now, if you solved this whole problem and you gave me the ortho, I'd probably give you most of the credit for this problem. It's important that you recognize that these NMR signals right here are indicative of not having a para-substituted ring, right? Because the para-substitution has some symmetry. This hydrogen is equal to this hydrogen, so we'd have the same signal. This hydrogen is equal to this hydrogen, we'd have the same signal. So we'd only have two signals of two H's each in the aromatic region, and here clearly we do not. I'm going to go to the carbon data next. And there's not as much to look at here in the carbon data. As we've counted before, there are 9 total signals. We have 9 carbons in our chemical formula, so we know that there's no symmetry in the molecule. The aromatics, well, this is probably the methyl, right? We know there's a methyl from the proton spectrum right here. 1, 2, 3, 4, 5, 6. There are 6 carbons here. That's probably the aromatic region. And here is the carbonyl region. And if we count our chemical shifts properly, we get 160. So basically 167, 169 are the chemical shifts here. And if you read from the table in your textbook, the carbon 13 signals table, we can recognize that these carbonyls will not be aldehydes and ketones because those signals appear around 200 ppm. So these are in the carboxylic acid or carboxylic acid derivative region, and we've already concluded that there was a carboxylic acid from the proton NMR data, and if you remember, we had this signal, or at least this part structure from the proton NMR data. We know now that that cannot be a ketone, so X is not a carbon group, but if you remember the formula, we had one final oxygen, so I'm going to propose that X is an O, and we have an ester here, and that would makes sense given our two carbonyl signals here are in the ester carboxylic acid amide region. So we have a carboxylic acid and an ester as part of our functional groups in our molecule. Let me go back to the proton spectrum now, and we'll put all the pieces together. All right, so let me add the ester here that we concluded from the carbon data. We already know that we don't have the ortho substitution pattern, so I'm going to go ahead and draw a meta ring here. I'm not going to put anything on the substituent positions yet, but we pretty much have all the data we need, right? Hopefully you've recognized that. We've got a carboxylic acid. It can only attach in one position. We've got an ester. It can only attach in one position. And if I attach these two together, I'd have a complete molecule. So that wouldn't really help us solve this problem. It wouldn't correspond to the formula. But of course, one of them can attach here, the other can attach there, and then I believe we'd basically be done with this problem. Let me fix my drawing here. So I got a carboxylic acid there, and then I have an oxygen, a carbonyl, and a methyl group. And so I believe that this is the complete formula. It should fit, I'm sorry, a complete molecule. It should fit the formula, 6 carbons, 7, 8, 9. I've got 4 hydrogens, 5, 6, 7, 8, and I have my 4 oxygens. So I believe that this is the best structure solution for this data.